Okay. Whoa. Okay. Now whoa. There we go. Okay. Okay. Good morning. How's it going? Okay. Okay. Good morning, everybody.
I had a quick question.
Yeah, we got about 10 seconds. Go ahead.
With regard to submitting homeworks, is it going to be on Gradescope?
Yes, and it's going to get posted onto Gradescope. Actually, you know what? Why don't I talk about that first? And it's time to start anyway. So here we go. So yeah, today is in fact, let me share screen. We'll go right over to the lecture schedule. So that was the perfect segue. So and of course, I always, as always, have to fix my. I should start doing this before class starts. Okay, so here's our lecture schedule. And homework one, you have noticed, I'm sure, that it includes everything that's going to be put into these 4 cells. And we just don't know what's going to be in this cell yet. And we won't know until the end of today. So, you know, after my last class today. So as soon as I finish that last class, then I will let my head grader know that it's, you know, what's due is determined, and that he can then create the item on Gradescope accordingly. Yeah. So of course now, you know, I hope you're already, you know, working on the 1.1, 1.2, and 1.3 exercises, and but yeah, you'll have a 2-day window for the actual submission on Gradescope. Yeah. Is that good? Okay, cool. Great. So let's see, we're already sharing. So let's go ahead and get into the material. Here's where we were last time. We were talking about section 1.5. We just barely started on 1.5. But here's the question we're going to start with. Suppose we're interested in describing a plane and we want to find the equation for a plane. Keep in mind, an equation is a point tester, right? So I want to find a way to test. Somebody's going to come to me with a point X and say, hey, is this point X in your plane? So what I know about the plane is that it is perpendicular to some normal vector and that it contains some given point X naught. And so question, given these two facts, given these two geometric objects, how do I make a tester? How do I test some vector X? Well, big idea is that if you want to test some point X, all right, well, that point X is in the plane simultaneous with this, let's see, color choices, with this vector being parallel to the plane, otherwise known as orthogonal. In fact, really, yeah, orthogonal to the normal vector is another way to say exact same thing. That we can write with algebra. Okay, so there's our tester. The way we test some point is does that point X satisfy this equation? Now it's a little bit easier to write it down. Well, it's a little bit more aesthetically pleasing, I'll say, to write it like this, but it's of course exactly the same thing. So this is what we call the equation, general equation for a plane. Right there. Okay, now I like it in this form myself, but of course you could actually crank out the dot product and write it like that. And then of course the right hand side, now keep in mind the n is given and furthermore the x naught is given. So everything over here on the right, that's all known. And so you crank out that dot product, you just get some number. Right. And so you could, if you prefer, write the equation of a plane like this. And that's also fine. And it has its merits. But there is something kind of nicely compact about this. Here we explicitly see the role that n plays, and we explicitly see the role that x naught plays. And I like being able to see what's going on. So I tend to like it in that form better.
I just have a question about this. So
Please.
I know that x naught is the point that we're saying is on the plane.
Yep.
X just an arbitrary point, but it's like we're writing it as XYZ. So when we expand it out, it's going to stay as XYZ.
Yep.
Okay.
Yep. That's right. So there's a convention that I use here, which is I tend to use the letter X to represent the vector XYZ, namely, the point that we're describing in space, the what tends to be the variable, right? The vector variable. If I were to describe x naught as a vector, I would put naughts on the subscripts like that. Yeah, good, great. Okay, so I will note there is something really nice about putting it in this form, and that is that keeping in mind that the right side of the equation is the dot product, and keeping in mind that, as per your question a second ago, the x, y, and z are the variables, well, then that means that the normal vector has coordinates a, b, c. You can just see them right there, right? And so this works two different directions. This is useful in two directions. If you know the normal vector, then you can write down most of your equation. Just boom, it's ax plus by plus cz. So knowing the normal vector is very, very useful here. But it also works the other way around. If you are not given the normal vector and all you're told is here's my equation, then you can infer your normal vector immediately. You're given this equation. What's the normal vector? Hey, no problem. The normal vector is ABC. So super handy fact about the equation of a plane. Okay, let's see an example. suppose I've got these 3 points, A, B, C, and I would like to find the equation of the plane. So there is a, assuming that those points are not all, like collinear or something annoying like that, right? Typically, generically, 3 points, they tend to kind of spread out in some sort of a way. And so they'll define a plane. What's the equation of that plane? Okay, so what do we have? We have the 3 points. What do we need? I want the equation of a plane. Well, to find the equation of a plane, I need to know the normal vector, and I need to know a point in the plane that I can call x naught to help me compute the right-hand side. Okay, so that's what I need. Let's start with the second part of that. Am I going to be able to find a point in the plane? Sure. I got a bunch of them. I guess I'll pick that one. I don't know. It doesn't matter. Pick any of them, any point you like. And this one is, you know what I like about this one? It has the smallest numbers, right? So, but if you just prefer to use a different point, that's fine. Any point in the plane will do. So what it really comes down to, what we really need is this normal vector. This is really the kind of the what's the holding up the show to just being able to write down the equation. So the way these kinds of problems tend to work out, here's a bunch of given information, find the equation of a plane, or find the, parameterize the line such that that kind of thing. You want to identify what it is that you have and what it is that you need, and draw a picture representing all of that. And then you get to start the puzzle of, okay, how can I use what I have to create what I need? And okay, so how am I going to make a vector perpendicular to the plane? And the clever insight here is to notice, of course, that if I know points in the plane, then I also have vectors parallel to the plane. And if I have vectors parallel to the plane, then I can use the cross product to make a vector perpendicular to the plane. So that's just a, that's how this particular one happens to work out most conveniently. Okay, how are we doing? Any questions? Okay. All right, cool fact. I think this is a neat one to observe. It's an easy one, but it's worth noting, and that is, if you have a plane, equation for a plane, and there are no y's in it anywhere, so the coefficient of y is 0 in the equation for this plane, then it turns out that means that this plane is parallel to the y-axis. There's a couple different ways that you can see this. Let me show you the most direct one first. No y's in your equation means this. And again, once you know the left-hand side of the equation, you instantly know what your normal vector is, right? I'm just reading off those coefficients, A, 0, and then C. So I know my normal vector. And knowing that normal vector has a 0 there instantly tells you that it is perpendicular to the y-axis. Right? And okay, well, yeah, but I also know that the plane is perpendicular to the normal vector. So if the y-axis is perpendicular to the normal vector and the normal vector is perpendicular to the plane, right? You got to think through the geometry, but indeed that does tell us that the plane has got to be parallel to the axis. Okay. All right, so this is what oh yeah, question.
Yeah, what exactly does it mean to be parallel to a line when you're a plane?
Yeah, there's a couple different ways you could say that. I think the easiest way to say it is that a line and a plane are parallel if they don't intersect. Right, and so that's kind of like, if you think about it, it's kind of like, well, parallel lines don't intersect. But here's a more direct way to say it. If you have a line and it is parallel to another line that is in that plane, right, then we would say that certainly the purple line is parallel to the blue line here. And the blue line is in the plane. Anyway, you can think about it whichever way you like. Okay, here's another way to think about this same result, and that is if there's no y's in the equation, and let's suppose I know some point that's on this plane, I'm just going to pick a point there that I know satisfies the equation. And now there being no y's in it, let me ask, well, what then would happen if I changed the y coordinate? For, start with a point that's on the plane. If I change the y coordinate, well, there's no y's in the equation. Change the y coordinate all you want. It doesn't change the equation at all. And so if you start at a point in the plane, and if you move parallel to the y-axis, then you end also parallel, at a point on the plane. And so if you know that moving parallel to the y-axis keeps you on the plane, then that line is parallel to that plane. Different point of view. What's nice about this one is it works for any sort of an equation. So for example, I'm just real quick, z equals x squared, right? What does that look like? Well, among other features that this surface has, it's parallel to the y-axis because there's no y's in it. Okay. All right, but that's a digression. We're on lines and planes here. Here's another little example. There's a million examples of this kind of business. So let's suppose we are given two planes. Oh, whoops, I'm in the wrong mode here. Two planes. So I'm going to draw myself a couple of planes. Whatever. And let's see, I want to, and I'm also given a point A, and I want to find, it says here, the line L that goes through A and is parallel to both of these planes. So paying parallel to both planes and going through the point A means it's got to look something like that. Okay. All right, so how will I parameterize this line? Now, again, let's think about what we have and what we want. I have some normal vectors, right? I can read straight off of these equations. I can infer those normal vectors right there.
Can you ignore the constants like 3 and 0?
Yes, that's that's one of the cool things. Yeah, the normal vector is just the coefficients on the left side. And so another way to say that is if you have planes that have different right-hand sides, they're all parallel because they all have the same normal vector. Yeah, it's a good observation. Yeah, absolutely. Okay. Yeah, so let's see here. We have these two normal vectors and we have the point A. What do I need? Well, this plane, to understand this plane, I need a point, excuse me, the line. In order to understand this line, I need a point in the line, which of course I'm given. But I also then need a vector parallel to the line because that's how we parameterize lines, is with a vector parallel to it. Okay, so what do I have and what do I need? Well, I have these things. I need these things. Obviously, the point is we're good. So said differently, I have these things and I need that thing. Right? I have two vectors perpendicular to the planes that are parallel to the line that I'm interested in. And so again, you got to think through the geometry and persuade yourself, geometric intuition unavoidably is going to be necessary here. These vectors must be perpendicular to the red vector. And so I can use then the cross product of these two green vectors to give me that red vector. How we doing? Everybody happy? Okay. All right. Now, I do want to give you all a warning. I used what I will loosely call kind of sort of transitivity sort of arguments about parallelness and perpendicularness. So, for example, most recently, I argued that these vectors, these vectors are perpendicular to the planes, and the planes are parallel to the line, and therefore, right? So there's kind of a transitivity sort of a thing there. And then likewise up here, the y-axis is, let's see here, perpendicular to the normal vector, and the normal vector is perpendicular to the plane, and therefore, right? So I just want to make a warning. Do be careful. Always think it through. Because not every sort of transitivity, not every one of these knee bones connected to the leg bone kind of geometric, statements is maybe as true as you think it is, right? So you do have to think it through. So for example, this vector is parallel to this plane. That same plane is parallel to that vector. So this is parallel to that, that's parallel to the other. It does not follow, right, that these are parallel to each other. It also doesn't follow that they're perpendicular. It's just, you don't get anything. There's no conclusion to be made there. So again, you got to think it through. And then likewise, here I have a plane perpendicular to another plane. And then here I have that plane, that plane perpendicular to a different plane, right? So P to Q, Q to R, but these are not perpendicular. Heads up, right? Think it through. Okay, let's talk about how to parameterize a plane. We've talked about the equation of a plane. Keep in mind, an equation is a point tester. What if instead, also for a plane, what if instead of a point tester, what if I instead want a point generator? I think it's a pretty satisfying argument that as long as you know some point on the plane, and as long as you know a couple of vectors parallel to the plane, here, let me just do it like this, parallel to the plane, then you can kind of play linear combination games. And so in particular, this point here, how am I going to get that point? I claim it's a kind of a combination of these. Well, I'm going to start with A. To A, notice I can add a multiple of V, and then to that I can add a multiple of W. And as long as I'm adding vectors that are parallel, given to be parallel to my plane, if I start in the plane, I stay in the plane, right? And furthermore, I think it's pretty easy to buy that you can get anywhere on the plane this way. So it's a very direct construction, and this is how you ultimately, this is how you parameterize a plane. And so good thing to keep in mind. By the way, there's a homework exercise in early on. I want to say it's in section 1.1, but there's a homework exercise that ultimately kind of uses this construction. So example, let's return to 3 points being given. How would I not find the equation? We already talked about the equation. How would I parameterize that plane? Well, to parameterize, I need a couple of vectors parallel to the plane. And again, you can just subtract pairwise, and sure enough, that gives you vectors parallel to the plane, and there's your parameterization. Okay, pause. Questions?
So going back to the first equation you had.
Yeah. Oh, you mean up here?
Yeah, so that one.
Oh.
So V and W are not necessarily in the plane, but when we multiply by the scalars,
Yeah.
is that what puts them in the plane?
No. So let me, I have to quibble with your language a little bit. I want to emphasize that this vector W isn't anywhere because vectors don't have locations. Right. So I'm drawing it there, but of course, W is just as it's exact same as that vector, which is exact same as that vector or that. These are all the same vector. A vector is just a direction and a magnitude. So the only relationship a vector can really have with a plane is to be, well, parallel or perpendicular or something like that. But vectors are never in or not in a plane.
So when we do coordinates, like, I don't know, 111 or, something like that, that doesn't really.
So, okay. Yeah. No, I hear you. So, and now keep in mind, there is an origin over here somewhere. Oh, here, let me do this in a different color so we can distinguish. There's an origin over here somewhere. And I can talk about, as you say, W's got coordinates, and those coordinates describe a point. Where is that point? That point is the point that you get by finding the arrow whose tail is at the origin, right? And then that point that you're describing is the point at where the head is there. And it's just at this point, it's just got nothing to do with what we're interested in, right? I mean, so yeah, sure, for every vector, there is a corresponding point. I'm not interested in that as relates to W. What I'm interested in about W is the direction that it points and not, where some point is that it relates to. I'm using W explicitly for its direction, and therefore I really want to think of it as a vector and not as a point. It's a great question, but does that make sense?
Yeah, definitely.
Yeah, cool. All right. Okay. So the last part of this section is what they call a bunch of distance problems, and it's just that there are some clever answers to some otherwise seemingly difficult questions that involve, clever arguments. And so I think it's a really nice feature of this book. I really like this book. They've taken some time and set aside, here are various kind of distance problems, and here's the tricks. Here's how you do them. So let's start with same place the book starts. We'll start with how to find the distance from a point to a line. So here's a point. Here's a line. And how do I find this? I'm going to use colors better. How do I find that distance from the point to the line? So there are different ways to do this. I'm going to show you two of them. The first one's kind of the most obvious one, and that is to say, all right, well, take some point x naught on the line, find that W vector, find its projection onto the line, and subtract, right? The difference there, this W minus the projection, is that dark green vector whose distance, whose magnitude tells you the distance, right? The magnitude of this dark green vector is the distance. So like I say, it's pretty direct, pretty brute force, and works just fine. Alternatively, and now here's a really kind of a more clever way to do it, and I think this is lovely, and it's very worth thinking about, and it could be useful for you at some point. Who knows? And that is to observe that this distance relates. Let's see. I'm going to try to say this strategically. This distance is relates to a quantity that I can compute in different ways. Let me highlight accordingly. This distance relates to a quantity that I can compute in two different ways. And this construction of, taking some quantity and computing it two different ways, and then therefore equating the two different formulas that you got, it's a really neat little math trick. We've already seen this pay off elsewhere, right? So of course, the quantity I'm talking about is area. So the area of this parallelogram here. So that area, on the one hand, I can compute it with sort of a height times base argument, right? Kind of a high school geometry sort of argument. And on the other hand, it's the magnitude of the cross product, right? If I were to look at these two vectors, right, and take their cross product, the magnitude is the area. Also, from last time. So not that I particularly care about the area, right? The whole point here, though, is that the area is just sort of an excuse to kind of start writing down a bunch of algebra, which involves the thing I'm actually interested in. And if the thing I'm interested in is involved, mixed up in a bunch of algebra I'm writing down, then I can solve for it. Well, hopefully, can solve for it. So this works great too. So take your pick. Honestly, I encourage you to try to be prepared to use both of these, because again, keep in mind, this is not a course about answers, it's a course about ideas. So the question, on an exam won't necessarily be, I'm looking for an answer and you're welcome to give it to me however you want. I might literally ask you, use the cross product to compute a certain distance. And then I specifically want this argument, and this would be not allowed. Okay. All right. Pause. Okay. Okay. So, yeah, distance between parallel planes. So parallel planes, such as these right here. They're what we call the distance between those planes is it's what you might call the perpendicular distance, right? So don't just pick any two random points, right? I don't mean what is that distance. That's not what we're talking about. What I mean is, for any given point, there's a bunch of other points down there. Find the one that's the point on the other plane that's the closest. That's what we call the distance between those two planes. Okay, parallel planes. So if you need to find that distance, the neat observation is real clever, but all you have to do is think of a difference and then use the normal vector for the planes to define a direction. And notice the distance that we are interested in happens to be that component. So it's a clever move, right? You make sure to remember this little clever move for how you compute that distance. Okay. Now, related problem. What if you want to find the distance between two skew lines? So this one's seemingly a very hard problem. You got a couple of skew. Keep in mind, skew just means that they don't intersect and they're not parallel, right? So two skew, like what I'm doing with my arms here, this is two skew lines. And how would I find the distance between them? And let me be clear what the distance actually is. Again, it's not just pick any two random points. It's find the point on the one line that's closest to the other line. In other words, you might say the distance between two skew lines is the shortest possible distance between those two lines. Okay, so how would we go about finding that? Beautiful idea is as follows. Two skew lines, whenever you have two skew lines, they are always inside of parallel planes. And in fact, how do I know they're inside of parallel planes? Well, I can take these two vectors V1 and V2, and I can cross them. And when I cross them, that resulting vector that I can view as a normal vector, well, it's perpendicular to both of the planes, and therefore perpendicular to both of the lines. So yeah. So neat fact. And then the question of, find this distance. Let's see here, this distance between the two lines, the shortest possible distance between the two lines. We just make the neat observation that that shortest possible distance is also, well, it's the distance between the two planes, these two parallel planes. And we already know how to find a distance between two parallel planes right here. So these are just clever little, clever people figured these out. And we get the benefit from their cleverness. So make sure you remember these tricks. Okay. Is everybody good? Okay. All right. So section 1.6 is another one of these sections that's largely review. It's a bunch of stuff about matrix algebra in there, for one thing. And y'all have all had Math 218. You should know all that matrix algebra. So I'm going to skip most of that. But again, you should be sure to review all of that linear algebra material that makes up, most of this section. So it's a significant section. And I've got, I think 3 pages of notes on it here of things that I think are, again, just the most important. And I want to remind you, that's how I put together my lectures. I'm not going to go through all of the book. I'm going to pick and choose how I can be most useful. What you most need, my point of view on, some examples, what have you. Okay. So real quick, I want to point out the triangle inequality. I'm just not 100% sure that this is actually covered in Math 218. It's a very innocent statement, really. Notice that if you have a couple of vectors, then in the process of adding them, you make a triangle. And the innocent statement is that this distance, namely the magnitude of, here, let me color code, the magnitude of the sum can never be any bigger than that distance, namely the sum of the magnitudes of the two input vectors. No side of a triangle can be longer than the sum of the other two. It just, right? It's just geometrically, it's, you might say it as the direct path between 2 points can't be longer than an indirect path between those exact same 2 points. So I think very geometrically satisfying. And as a statement about vector algebra, it looks like this. So again, hopefully you've seen it before. If not, there it is. Cool fact. There's other facts about vector algebra, the Cauchy-Schwarz inequality, which of course is very standard. It's noted in the book. Make sure you remember that. Again, I'm going to pick and choose carefully. Okay, here's one. Again, I think you've probably seen this in Math 218, but I use this fact a lot. Excuse me. It's just an observation about how to multiply a matrix times a vector. And I know y'all know how to multiply a matrix times a vector. But there are different ways to multiply a matrix times a vector. And I think this one tends to get underappreciated. Golly, excuse me. I think it's underappreciated because students are so easily sold on the idea that you just do dot products, row dot column, bam, and you can just kind of write it down, and it's numerically, it's sort of super convenient. Well, let me remind you, don't be too sold on the mere question of how useful is this for me to compute stuff, right? Because look, computing stuff is important. Don't get me wrong. Absolutely. It's very important, but it's really not the whole picture. What we are interested in here is ideas. And so the fact that this is computationally convenient, yeah, that's nice. What else you got? Why else is this useful? How does this help me understand ideas that are going to relate to other ideas? What connections does this make for me? These are the kinds of questions that we should be thinking about. Now, this observation again about, row dot column does have cool connections. This connects to dot products. Dot products is an interesting construction. So I'm not trying to talk you out of this point of view. I'm trying to talk you into that there are other options that have merits that this doesn't. So the one I want to pitch here is that when you multiply a matrix times a vector, what you're doing is you are taking a linear combination of the columns of the matrix. So matrix vector product is a linear combination of the columns of the matrix. And specifically, it's a linear combination where the vector that you are multiplying by, its coefficients, its coordinates are what give you the coefficients in that linear combination. Okay, I think this is a huge fact. Super big deal, very, very useful. So matrix vector product, it's not just dot products, it's also linear combinations. It's not just that the rows of the matrix are interesting. The columns are interesting too. So this is more connections of matrix vector product to other interesting things. And again, really underappreciated. This is one of these things where, very, very often, I don't know, I think certainly coming into college, very few students have even seen this. Whereas most students who take a linear algebra course have previously seen the dot product. Okay. Pause for questions. Okay. All right. I want to remind y'all what linear transformations are. And again, I think you already know this. It's just that this is where the book says it. So I'm going to go ahead and take that as an excuse to talk somewhat at length about this. Again, this is really a fundamental fact for Math 218 is this idea of linearity, a function being linear. And the big idea of linearity, the way I like to think about it anyway, is that when you put a linear combination into a function, you get the corresponding linear combination out from the function. That's the way I like to say it. Linear combination in, linear combination out. Now, to be precise, if you have a linear combination of inputs, then its image is the same linear combination of the corresponding outputs. Okay. Okay, now this is one of three ways to write that condition that is entirely equivalent to this pair of conditions. And if you prefer to write it that way, cool, it's great, no problem, exactly equivalent. Sometimes it's useful to think of it this way, that in other words, that you could have any number of vectors in the linear combination. Very handy. And also completely equivalent. So take your pick between these three options, or more to the point, be sure that you're clear that at any given point in time, you may and possibly will need to choose any one of these three. Okay.
Why is B a vector in the first one?
Oh, because I brain spasm. I screwed up. Thank you for noticing that. I'll get that fixed. Let me scratch that off in red. Thank you for noticing. Silly me. I don't know what I was. That's just, my finger. I'm going to blame my fingers, not my brain. Yeah, so I'll get that fixed. Thank you. Anybody else?
So would the function t represent like a form of matrix vector multiplication?
That's a great question. So you're actually getting a little ahead. I'm going to come back to that in a minute. Right now, I just want to think of it as being a function. No comment as to whether any possible connection between it and matrices. But good. I mean, ultimately you're right, yes. But for the moment, I just want to be broad, and this could be any function that satisfies these properties. Okay. All righty. I'm going to show you some examples. Oh, and then remind you of the terminology. You can call this function linear. You can call it a linear function, but be aware that this term linear transformation is also very popular. And it's a linear function, but you'll hear people say linear transformation. Okay. So some easy examples. And again, I think you've probably seen most of these before, but if you have some vector in Rn, you can use that. I'll say dot product with that vector to define a function. So what you do to a vector X, what P does, what does P do to a vector X? Well, it dots with the given vector A. This function is linear. And that's something that you can directly check using these properties. Take your pick of either of these three properties. I like number one myself. So that's a good practice problem. You want to make sure you are still good with doing that. I, again, presume that you did things like that previously, but it's a nice warm-up exercise. Here's one that's maybe a little bit less expected, and you might not have seen this before. In fact, I wouldn't be terribly surprised at all if you hadn't seen this. But the same thing is true of cross products. Using cross product with a given fixed vector is linear. Okay. And here's one that's oh gosh, I dare say I think you almost certainly saw in Math 218. This is an important property about determinants, and I know you all have seen a lot about determinants before. This is what's referred to as the multilinearity of determinant. And the way I'm going to say it here is that if you have a bunch of vector, n minus one vectors given, you can define a function with that. And specifically, the function is the function which acts by, you give me a vector x, I make it the last row of this matrix, and then I compute the determinant. So all that we have together in blue allows me to say, if you give me a vector x, I can compute some stuff and get a value. And that's what D does. Okay. So this function is linear. Again, it's important that determinant has this feature, multilinearity. By the way, I put the vector here in the last row. It could have been any row. It could have been any column, right? If you just kind of arrange things accordingly. So determinant is multilinear in every row and column. And again, very powerful property of determinants, and good to know. Okay. All right. Let's see here. Oh, by the way, we started at 10:15, so I have it till 11:05. Okay, we're doing great. Somebody asked a minute ago about this, and I think a really important fact, one of the most important facts really about linear transformations, Euclidean linear transformation. So from Euclidean space to Euclidean space, is that they can always be represented with matrices. So if you have any linear transformation, then there is a matrix that represents it in this sense. In other words, you can always think of any linear transformation on Euclidean spaces as well, you're just multiplying by a matrix. Effectively, you're just multiplying by a matrix. So, all right. Now, so I'm saying furthermore, I'm saying these two statements are equivalent. The up direction of this is actually pretty straightforward. Up means that I get to assume that I have a matrix, and then I get to assume that I'm defining T like that. And then I just have to prove that T, for which I have a explicit formula, I just need to prove it's linear. And so all I have to do is plug and chug into these properties and just, does it satisfy this property, and just multiply it out. Sure enough, it does. Okay, so that's what I'm going to call direct computation. The other direction is where it gets interesting. So how do we show the down arrow? So how do I show, therefore, just knowing that I have a linear transformation? How do I know that there is a matrix? I'm not even given a matrix to consider. Where am I going to get this matrix from? Right? I need to show that I can find a matrix, and furthermore, that it has. How do I know that I can find a matrix that has this special property, that it computes my linear transformation for me, right? This linear transformation that I'm given. So hard, because again, I don't know how do you get started, right? So really clever idea. I hope you all have seen this before, but if not, I mean, this is a really clever concept. And that is, first thing I'm going to do is say, all right, well, I need to, by the way, let me come back up here. I need to compute T of X, right? I'm hoping that I can get it to turn into matrix times X. So I'm going to start by taking T of X, and let's see what I can figure out about T of X. And specifically, what do I know? How am I going to get started? Well, all I know about T is that it's linear. So let's try to use linearity on this left side of the equation and see where that leads us. Okay, well, the vector X, this vector X is a linear combination of the standard basis vectors, right? In other words, coordinates are coefficients in linear combinations of the standard basis vectors. Now I've got a linear combination, and linearity immediately tells me that this, here I'm putting a linear combination in the transformation. Here I'm saying that what comes out is that same linear combination of the outs. Okay, so this is the linearity right there. So what I've shown, not done yet, but I've shown that T of X is, it's a linear combination. What I'm trying to show is that T of X is a matrix vector product. So I know that it's a linear combination. I want it to be a matrix vector product. Sure is handy that we know that matrix vector products are linear combinations, right? And so with that observation made, that pretty much tells us what to do with this. I say, okay, well, I want to connect this to matrix multiplication. So I need to make these things here. I need to make those the columns of my matrix. So I make that choice. Now I've got this matrix A, whose columns are those images. And all of these turn into A's. And my linear combination of the T's turns into a linear combination of my columns. And that's exactly, well, I guess I'll just, that's fine. That's exactly AX. Okay, really cool proof, very clever argument, very powerful result. Yes, every matrix is linear, but more importantly, anything linear on the Euclidean spaces, anything linear is a matrix. And furthermore, here's your fancy formula for how to do it. Here's explicit instructions for how to find the corresponding matrix. The columns are the images of the standard basis vectors. Okay. All right, let's see, where am I? I am technically out of time. Oh gosh. All right, I'm out of time. We'll draw the line right here. God, we're so close to done with 1.6, but I know, side note, I'm not as far along in my other sections, so I know I'm not going to finish 1.6 in the other sections, so we don't need to rush to do it ourselves. So yeah, I guess I can go ahead and call it then. Where the almost certainly the homework is going to go through section 1.5 for homework 1. But technically, I do have to wait until I finish the other sections. Y'all have a nice Wednesday. See you Friday. Good luck with the homework exercises. I'll get that posted onto Gradescope. Hopefully by the end of today, if not early tomorrow. See you later. Have a good one.
Thanks.
Thank you.
Thank you.
I kind of am a little bit confused on the concept of like what linear means.
Okay.
Like,
Yeah. So you that's a great topic. And the thing is that I've got office hours in a couple of minutes,
okay.
and it's going to be a little bit of a long discussion. I mean, there's just a lot to say about that. Are you coming? Can you come to office
Yeah, I
hours?
can come.
Great. Let's talk about it then. And also then we'll have the advantage of not being recorded.
Perfect. Thank you.
Yeah. I'll see you in office hours.
Bye.
Yeah.